Astronomy Cast, episode 282 for Monday, November 26, 2012. Seasons. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hey, Pamela, how you doing?
I'm doing well, just shivering a little bit,
Yes.
which somehow seems appropriate for discussing the seasons.
Yes, exactly. Yes, we are recording in very cold places in our houses, and that's going to come through the recording. So we're going to try and keep the energy level up, ask very warm questions. So
And we're acutely aware of the changing seasons in our northern hemisphere homes today.
yeah, so one thing that I would like people to know is, as always, we record this episode as a live hangout on Google+. And so you can come, you can watch us record the episode live. But one of the cool things that we do is we stick around after we do our recording for about half an hour or so and answer questions and, sort of continue the conversation. And we're happy to both answer and discuss the topics that we're talking about in the show, but also just anything about space and astronomy. If you have some weird what-if scenarios that don't require too much math, we can throw them at Pamela and just demonstrate her massive brain.
And traumatize me in the process.
Exactly, yeah. We don't go easy on Pamela during that second segment. So, but if you want more of the show, you want more of us, you want more of sort of space silliness, then that's a great way to kind of get more out of it. Now, you can always, if you miss it live, you can always just watch it on YouTube as well. So, although the podcast, the tight 30-minute, 25-minute podcast goes out on our podcast feed, the full video is recorded on YouTube, and you can find that there. And I think people can get that on the CosmoQuest site, right?
Yes, it's all archived through CosmoQuest, and if you search on CosmoQuest in YouTube, you'll see a channel called Astrosphere Vids, and that's our host channel for everything we do at CosmoQuest.
Yeah, and there's a beautiful archive of all the different projects that we work on. So I highly recommend, if you want more of the Astronomy Cast, then that's a way you can get more of it. Okay, great. All right, well, let's get rolling. So spring, summer, autumn, and winter, these are the seasons that we experience here on Earth as our planet completes an orbit around the sun. But what's going on? Why do we experience such different temperatures and weather over the course of 365 days? Do other planets experience the seasons like we do? So if I recall correctly, the seasons happen because the Earth is moving closer and further away to the sun, right?
No.
No, that's wrong.
No,
but that's what most people believe.
I know, and it's such a disturbing idea, because how does that work with the northern and southern hemispheres? Because really, we can't. It just doesn't work. Mm-hmm. So I think people are just like not aware that there's two halves to our planet or something.
Right, people don't think through the implications of what's really going on. Okay, fine.
Right.
So that is not what's going on. It is not the Earth getting closer and further from the sun over the course of its orbit.
We're actually closest to the sun in the beginning of January. So those of us in the northern hemisphere, when we're shivering after the New Year's, we're closest to the sun at that point.
That's true. Okay, so then what's really going on? What is the cause of all of this seasonal madness?
At its most simple, it's a matter that as the planet orbits around, we're keeping our northern pole always pointed at the same star in the sky, Polaris, plus or minus a degree, and the butt end of the planet, southern hemisphere,
the important half of the planet are
always pointed
wonderful southern hemisphere listeners
at the same set of stars in the southern hemisphere. And in order to maintain the planetary alignment relative to the stars other than our sun, as we go around the sun, we're actually orienting different parts of our planet toward the sun. So if you live in the extreme north or the extreme south, you know that during your summer, the sun may never set. And this is because your part of the planet is pointed towards the sun, such that as the planet rotates, the sun never gets below your horizon. And in the winter, the sun may never come up, or it may only come up for a brief period of time because you're almost exclusively in shadow. So this is the problem, that you have planetary tilt, and then you have that dividing line of where the sunlight is hitting. And the sunlight hits the half of the planet that is oriented toward the sun, and if the North Pole is in that half that's oriented towards the sun, that half that is being illuminated by the sun, well, that that's where the sun will never set. Now, 2 days of the year, the equinoxes in March and September, these are the days when the North Pole lines up with that line between sun and shadow cast on our planet, and the South Pole lines up with that same line. And this means that our north and south poles are exactly at a right angle to the sunlight coming at our planet. And that means that on those days you get both sunrise and sunset on the two poles. You get equal amounts of daylight and nighttime. But the rest of the year, pick a pole, it's going to be pointed at the sun if you pick the right one.
And I think one of the things that causes people a lot of problems is just this concept of, I mean, they can understand that the Earth's axis is tilted, and so they can imagine, instead of the Earth spinning straight up and down, that you actually, like a gyroscope. You've ever played with a gyroscope? Or have you ever been in like one of those science experiments, like it's in like a science museum, and they give you like a big bicycle wheel to spin,
and you try and spin it, and the chair you're on moves instead. Yeah.
Right, and so you can turn it one way or turn it another way, and you can kind of feel that. You can feel that centripetal force, but you can also sort of see that that's what it would be like. If you held that bicycle tire where the handles are pointing up and down, that would be as if the Earth had no tilt. Turn it a bit to the side, and now you've got that slight tilt for the Earth's axis. But I think the part where people really go wrong is how it's on one side of the Earth's orbit, of the sun. It's pointed towards the North Pole, towards the Polaris, and then on the other side of the orbit, it's still pointed in that same direction.
Right. Earth is always pointed in the northern hemisphere, roughly towards Polaris, and in the southern hemisphere, roughly towards a small triangle of stars. And the other place where they get very confused is when we say that the seasons are because we are oriented with a pole more closely aligned towards the sun than during the other season. Well, if the North Pole is at its most aligned toward the sun in summer, well, doesn't that make it closer to the sun? Well, yes, but it also makes me closer to New York if I lean backwards in my chair, because I know New York is that direction. Now, the difference between here and my head in New York City, not a noticeable amount. And the difference in distance between New York City and the sun, between winter and summer, it's not defined by the tilt. The distance is much more defined by the ellipticity of the Earth's orbit. So it's a matter of proportion. It's a matter of what matters. And that distance change between being pointed towards the sun and being pointed away from the sun, it really doesn't add up to a noticeable amount. So this leads to the whole confusion of why is it colder in the winter?
Mm-hmm. Well, and there's a great science experiment that you can do that really nicely illustrates that, is to take a flashlight and to aim it straight towards, say, like a piece of paper, and you'd call that summer, but then aim it at an angle, and you would call that winter. But you can see that the amount of space that the flashlight is illuminating is much larger, but it's still the same amount of light coming out of the flashlight.
And this is somewhat not as easy to understand with modern LED flashlights. With the old incandescent ones, you could hold them close to your hand and you could actually feel the warmth, and as you tilt the light and spread the light over more of your hand, it's not hot anymore. But you can actually, if you have a green laser pointer that is illegal, one of those ones that you should absolutely not point at the sky, but you can buy on the internet. If you take one of those green, and I know that many of you, yes.
I love my green laser. Anyway.
If you take one of these green laser pointers and you take a bar of chocolate, a nice smooth bar of chocolate, if you hold the laser pointer so that the beam is as small as possible, so the pointer is exactly perpendicular to the chocolate, you can melt a divot in the chocolate because of the heat of the green laser beam. Now, if you tilt the laser so that it's almost a glancing blow, and you see this large green blob of the light getting spread out across the chocolate, you might eventually be able to melt some chocolate, but the intensity of the light, it's just not concentrated enough to have a quick melt effect. So this is a meaningful experiment using a laser that you shouldn't let children play with. This is a meaningful experiment that allows you to see if the light is focused over a small area, all of that heat is concentrated and it warms it up. If that light is spread over a larger area, you're trying to heat a larger area, and it's just not going to be as effective. And it's that efficiency in heating that goes down in the winter.
Right, and so the sun is only putting out a set amount of photons, but those photons are having to spread across a wider area of the Earth, and so you're getting just less heat.
And
So
in
it's
this particular case, the light coming out from the sun is far bigger than the planet Earth. And so what's happening is at the pole, not at the pole, at the line where it's the midpoint of where the sunlight is hitting the Earth. On the equinoxes, this is the equator of the planet. Right there, the sunlight is hitting straight down, so it's getting concentrated nicely. But as you hit the more and more curved parts of the planet, the light has to spread out to cover that tilting surface. And you can do this experiment with a big light. If you hold the board straight up, as you tilt it more and more and more in that light, you'll see that it gets fainter and fainter.
Yeah. So that's sort of why the seasons are happening, but yet we don't really experience the seasons here on Earth in this really sort of absolute stark way. Like the coldest, I guess, well, for example, like the longest day of the year, the day that's getting the most sunlight for the northern hemisphere is what, June 21st, right?
Right.
The summer solstice, and yet that's not the hottest days of the year. The hottest days are usually coming in July and August. So why is there that delay happening?
It's the same reason that I can walk up to my steam radiators in this old house I live in, and even though the heat is off, they're still warm. It's because our planet is able to hold on to that heat and continue radiating it out. Now at the same time, it absorbs some of the heat. So what ends up happening is we have the sunlight coming down, hits the planet Earth. Earth absorbs a lot of the different colors of light, re-radiates it as infrared, which we perceive as warm. Now, in the winter, it's radiating away the heat faster than it's absorbing heat. So this means that it's basically going to end up giving up all of its heat by the end of winter in some places, or at least a lot of its heat. It doesn't become like a Bose-Einstein condensate and hit absolute zero. It simply gets cold.
That would be bad.
It would be bad. It really would be bad.
Yeah.
So the soil, the bodies of water, many different heat sinks, they radiate away the summer's heat during the winter, during that first part, allowing us to have fairly mild falls, allowing the longest day of winter to not be the coldest day of winter because the ground is still radiating out that summer heat it absorbed. But by the time the end of February and March comes along, a lot of that heat has been given up to the air. And so when the days start getting longer again after the March equinox, we're now at a point where the soil is trying to warm back up, but it's not re-radiating a lot of heat. Come August, we have sunlight coming down, and then we have the ground re-radiating up at us. And so it's that combined heat of the planet and the sun that makes August such a miserable month.
It's a wonderful month.
It's the dog days of summer. The
Right.
dog sitting in the grass, tongue lolled out, being lazy. That is
Yeah.
my image of summer.
Yeah. So now for you and I in the northern hemisphere, we've got these really distinct seasons. We've got well, I guess maybe not me on the West Coast. I've got a rainy,
Those
a
of us
rainy
who are
fall.
far enough north.
Yeah, far enough north. Yeah, I have a rainy fall, a rainy winter, and a rainy spring, and then a hot, dry summer. So that's the best I can do. But for a lot of people, in the northern hemisphere and far enough in the southern hemisphere, you get these distinct seasons. But for a lot of places closer to the equator, they really don't experience seasons in the same way that
No,
places like us do.
and
So what's going on there?
so here you basically have the sun bouncing back and forth between a narrow set of angles in the sky. So in the northern hemisphere, where we are north of the Tropic of Cancer, north of Florida, basically, where we are, the sun never becomes straight overhead, but it goes from fairly low on the horizon to midway up the horizon to slowly getting closer and closer just straight overhead as you move further south. So for us, the seasons are defined as in summer, the sun is at its highest point in the sky. In winter, the sun is at its lowest point in the sky. So this argument that the seasons are caused by how directly the sunlight hits the earth makes perfect sense. Now, if you happen to live on the equator, on those equinoxes, on those days in March and September, you have the sun straight overhead. And as you go into the extreme southern hemisphere, you end up with the sun lower on the southern horizon. As you go into the extreme northern summer, you end up with the sun low on the northern horizon. And so you actually find that in your December and June, that's when the sun is lowest on the horizon. So the sun is constantly bouncing between these 2 points that are both pretty high in the sky, and
Right.
you just never get any relief. So when
And
you
it's
live in that
always sending out
band,
energy. Yeah.
yeah, it just
Uh,
makes for a miserable lack of geometric relief from the sun.
I think I can remember being in Mexico one time, and I guess it was in December, and seeing the sun that high up still was really
It's
unnerving to me.
confusing.
Right? Because, I'm so used to the sun taking this long, low path across the southern horizon, like, especially like now, as we're
Yeah.
nearing December, we don't get much sun. Sun gets up, in Canada, right? The sun rises around 9 o'clock and does this very low to the horizon across the entire day, and then probably sets around 4:30 or so.
It's
So, very little
yeah.
sun.
Travel opens you up to understanding the sky. Last Christmas, my husband and I made the discovery that the transatlantic cruises aren't that expensive when compared to a lot of other things during the Christmas period, and so we ended up sailing from Gibraltar down to Rio de Janeiro, and as we made this journey that crossed the equator, we watched Orion going from standing up to standing on his head. We watched our days go from short to long, and the temperatures changed, and it was just this dramatic example that we live on a globe.
Hmm.
And you have to just imagine how confusing and perhaps even terrifying this was to early sailors as they took off from northern latitudes like England and then sailed the Cape of Good Hope. It's our planet is extremely varied, and you can find almost everything on any given day of the year.
Now, like with many things in astronomy, our current experience of the way things are is not the way things have always been. There are cycles going on that actually change the way these seasons are experienced. There's one, I forget, like, is it Milankovitch cycle?
Well,
There's,
it's there's a lot of these different cycles,
yeah.
and they have many different names, and they basically boil down to three different things. One, there's some sort of cyclic cycling of our atmosphere that we don't understand, that probably is some interplay with volcanoes and other things like that are our Earth affecting our atmosphere. There are additional cycles, however, that are caused by our Earth's pole slowly precessing, just as tops precess, but then our planet is also getting torqued, which is a fun word to say, is also getting torqued by its interactions with other worlds. So over time, the orientation of our rotational axis is changing. And as that orientation changes, that changes the geometry between us and the sun. It changes the angle at which the sunlight hits the planet Earth. And in effect, it changes how intense the light is on different parts of our planet throughout the year.
Right. And so like that that cycle is, some of those cycles are quite long, right? Like
Hundreds of
13,000
thousands of
years.
years.
Yeah, I think
Yeah.
one is like 13,000 years for essentially for the seasons to flip, right? For you to
Well, they
get
never completely flip, but they do change radically.
Now you mentioned, like right at the very beginning, that in fact the Earth is at the northern hemisphere is at its closest point to the sun
The
in
first week of
January,
January, yeah.
right? And then it's at its most distant point, I guess, in what in the northern hemisphere's opinion is
And this
summer.
does actually have a small effect on how different our two poles are.
Right.
So the southern pole is not undergoing the same complete glacial melt that we're seeing in the northern pole, where you can now safely take cargo from Russia to Alaska in the summer.
Yeah.
So
So
yes,
this is
we
one of the
do.
reasons why Antarctica is just a lot colder, a lot more, more temperature extremes than the northern
And the fact that
pole.
it's land also changes the thermal capacity.
Yeah.
Where
Yeah.
we really see this much more markedly is on Mars, which has a tilt not too different from the Earth's tilt, but its seasons are more exaggerated because its tilt is just a bit more exaggerated, and the entire world, well, it clearly doesn't have oceans the way we do, at least not today. And so we do see much more difference between its northern and southern poles.
And then, this is perfect. I want to talk about some of the other planets in the solar system because, as you said, Mars has a very similar axial tilt to the Earth, and so they get these same kinds of
Yeah.
seasons. But some of the other planets are a little more extreme. Saturn has seasons, right?
Saturn has seasons. The Cassini data has been absolutely fabulous because we've now gone through equinox, and so we've been able to see storms spin up and spin down in the hemispheres. We've been able to see what we think might be the equivalent of moisture fall, for lack of a better phrase, on Titan as the seasons changed on Titan. Our thermodynamics shows no mercy. If you have a tilt, you have seasons, and that's kind of awesome.
But then you get a weird situation like Uranus, right?
Well, so Uranus is the planet that fell over. Basically, this is a world that it twice a year for its years, which are tens of years, tens of Earth years long. Um, it will point its north pole pretty much exactly at the sun, and then it will point its south pole pretty much exactly at the sun, and this leads to massive storm differences. It leads to very strange dynamics in how you have to try and model its atmosphere, and it's just a very different world where imagine half the planet went to night and half the planet went to day, and you're still rotating, so you're still getting the winds that are driven by planetary rotation. It's just a very different, very interesting world. And then just to mess with us, there are worlds like Pluto where the seasons are defined not by axial tilt, but by the fact that it actually does get significantly closer and further from the sun.
Right, right. So
So
that does
yeah.
play an effect. I mean, if you've got a really elliptical orbit, you're going to get the situation where the distance to the sun is going to play into your
But you
temperature
have to
extremes
have a
with your seasons.
seriously elliptical orbit. Comets are an example of the extreme of this, where they don't exactly have tails in the outer solar system, and you can view their heated up and expelling a tail as summer. Um, they may have tilt depending on which one you look at, but that doesn't matter. What matters for them is distance from the sun. So
Yeah.
planets, for the most part, planets according to the modern definition of planets, don't have very elliptical orbits, with the exception of Uranus and Neptune. Um, they're pretty much round. Mercury is another annoying, not as round as one would want, but round enough.
Yeah, I think it has one of the most roundest orbits, so and not a lot of tilt. But and of course now we're in this modern age where what like 500 extrasolar planets have been discovered, and so
And
we're
there's
starting.
there's evidence for upwards of 1,000 that still need to be confirmed. So
Yeah, and so we're finding again these concepts of seasons are now starting to extend out into these extrasolar planets. You've got worlds, these hot Jupiters, which are tidally locked to their sun. I mean, what would a
right.
season feel like on a planet like that? No season, right?
Yeah, not so much. If you're tidally locked, the part of your planet that is getting crispied is going to stay the part that's getting crispied, and the part that is pointed away is probably going to have its own effects to deal with. So tidal locking is definitely one of those bad things for seasons when you're tidally locked to a star. Much better to tidally lock yourself to another planet like our moon has done.
Right, right. And then imagine some of these worlds that are, in binary star systems, the Tatooines, where you would probably get these really complicated seasons with,
Well,
you
it
know,
depends on how the orbit is. If you think about it, as you get significantly far away from the other stars, they aren't going to really impact your seasons. So if you're orbiting close in to your host star and the other two stars are significant, or one star is significantly far away, it won't play any more of a role in the seasons than I don't know, the moon's reflected light plays in the seasons.
right. So there's just not a lot of energy coming out of these other stars in
Right.
the system, right?
And the other situation is you have close in binary stars with planets orbiting the set. So in that case, again, if you're orbiting both stars at once, yes, the amount of light you get will depend on how those two binary systems are or aren't eclipsing one another. But again, that's not going to be necessarily what dominates your seasons, depending on distances. It's geometry allows all options, and so you can have crazy seasons if the stars are close in and you're between the two of them in a chaotic orbit. But then you can also have nice stable seasons that have some variation, but not that crazy, simply because the stars are significantly far apart or significantly closer compared to the distance to the planet.
And you can have a situation like Venus where the atmospheric effects are so powerful that they really just override any seasonal variations that you would feel.
Right. This is the case of um, everything that comes in does not get given back up to space. So you have such good, essentially one-way insulation on Venus that the sunlight passes through the clouds, and then when the infrared radiation tries to escape back into space, that atmosphere says no. And that atmosphere causes the entire planet to basically remain as a giant heat sink that keeps the atmosphere hot beyond what you would get without the atmosphere, 900 degrees Fahrenheit.
So I got one last weird question for you here, which I know are your favorites. Does the moon experience seasons?
Um, it doesn't really have that much of an atmosphere.
Right, so it doesn't have the atmosphere to trap the heat, but if you lived on some base on the moon that maybe wasn't in one of these, permanently dark craters, would you experience seasons in the same way?
So the thing with the moon is it goes around the Earth every month, and it's during that month that it changes how it's oriented towards the sun. And there are slight librations rather, that cause some of it to point more towards the sun, some of it to point less towards the sun. And when you do thermal maps, this can crop up in how heat is dissipated, but we're still trying to understand this. We're still doing the thermal maps. We're still trying to figure out what heats up for long, what retains its heat longer, what doesn't, how do all of these different things interplay. So stay tuned for more data
Yeah.
to come down.
Definitely, would want to go into your calculations if you wanted to set up your solar panels and collect your energy on the moon, right?
Well, so there it's a simple matter of put your solar panels in an area that's eternally lit on either the northern or southern pole. That's an easy calculation.
Yeah.
And for the majority of the planet, it's not planet, for the majority of the moon, it's going to be half a rotation of sunlight, half a rotation of darkness, and you just don't get around that.
Cool. Okay, well, thanks a lot, Pamela.
Thank you. Okay, saving.
Stop. Save.
It's very weird having my monitors vertical from one another. I'm sure I look something like a crazy person. There we go.
Export that too. Okay, so we're gonna
My
we're just gonna
coffee cup is cold to the touch.
yeah, mine is too. So we're going to stick around for another 20 minutes, half an hour or so, and so we'll answer some questions, and any questions that you have about space and astronomy, we're happy to jump on that. So as I mentioned at the beginning of the show, you can post your questions on Google Plus, on the event page, in the stream if you're watching it there. If you're watching this somewhere embedded, you can use Twitter with the hashtag AstronomyCast, or you can do it on YouTube, and the safest place is YouTube.
Please be one of the decent commenters on YouTube. Show the trolls what real comments look like.
Oh. Okay, I'm safely exported.
Yeah, my attic is like 18C.
Okay, so here's a question. David Haley asks, a little off topic, but is a comet's tail due to solar wind? What causes the drag and push to make the tail long like that? Comets. Have we done a show? We did a show on comets.
I don't know. We've done 280 shows. I can't remember anymore.
Yeah.
So the sun has this constant flux of light, clearly, and particles coming off of its surface. This is the solar wind. And that solar wind has enough strength to, well, it reshapes the Earth's outermost magnetic field lines through the interactions and many other things. And one of those interactions that it has is when the sunlight hits the comet, it will melt if the comet is close enough to the sun. And by melt, I mean convert from frozen gas to gaseous gas, the composition of the comet, and then push that new gaseous material out in a straight line from the sun through the comet and outwards. This is one of the neat things, is people often have this misconception that the comet tail stretches out behind the comet relative to its motion. But the truth is that the tail always points exactly away from the sun. So you can draw a line through the tail to the sun.
Right. So when the comet is moving towards the sun, the tail's pointing away. When the comet's moving away from the sun, tail's pointing away. And we might get an amazing comet this year.
Yes.
Next year. This time-ish next year, we may or may not be watching one of the brightest comets in living memory.
This is one of the problems with comets, is they're the great deceivers. Because you never know, are they going to shatter, or are they going to melt off the layer of nice gases and leave behind an organic sludge that doesn't form a tail? There's so many different variables that go into whether or not comets are bright and beautiful or duds, and so we don't know.
And so we've got this, this comet, is Comet Ison, I think it is on this really great orbit, but as you said, we don't really know what the consistency of this comet is, so it may just hang tight like a little ball of rock and not do anything interesting, or it might just get, jiggled up by the gravity of the sun and torn apart, and could form this amazing bright object that might be one of the brightest comets like we've ever seen. So this is next year. So it could be anywhere in between, anywhere from nothing to the best comet anyone has ever seen. That's the scale. So, so we did episode 19 was about comets. Now, Umu45 asks, have we done a show about the moon? Yes, we have. Yeah. We've done several shows. Episode 113 is called The Moon. Episode 114 is called The Moon Part 2. Episode 115 is called The Moon Part 3. Episode 17 is Where Does the Moon Come From? And episode 234 is Lunar Phases. So, yeah, we've done quite a lot.
We have a moon problem.
We have a moon problem. Let's see. Okay, here you go, Pamela. Mr. Activision78 wants to know, what is a Bose-Einstein condensate? Since you mentioned the possibility that our atmosphere and Earth could turn into a Bose-Einstein condensate.
So if you get something like I don't know, various gases cooled down to the point that they become liquid, and then you keep removing heat from them. And normally you don't talk about removing heat from something, but in this case it's a combination of magnetic fields, and various pumping actions are used to basically stop the motion of the atoms, and that stopping motion equals removing heat. And when you stop the motion enough, the way the gases behave stops being like a normal gas, becomes a liquid, stops behaving like a normal liquid, and becomes this weird stuff that will do things like climb out of the container that it's in as it spreads itself out, and many other weird physical properties. We did an entire episode on this, so I'd encourage you to go listen to that episode.
Right. Okay. Someone noted that you talk with your hands quite a lot.
I do. I do.
You do. This
Especially
is the thing
when I'm cold and trying to stay warm.
This is the big revelation that we've had since we've been doing these video things on Google+. I don't think people realize just how much of a hand talker you are. So, KKM121 wants to know, is there any progress in saving NASA's planetary science budget? Wah, wah. Where's that at?
Well, it's the wrong point in the budget cycle for anyone to know anything. Ask again in March. We should have more information in March.
Yeah. Sad. Okay, Iwan Timmermans says, is it true that Saturn actually has a solid core?
Unknown, probably.
I mean, with Jupiter and Saturn, right, there's enough material and there's enough rocky material in these planets to form several Earth-sized worlds, but the question is whether or not they're rocks, I guess.
Well, and rock isn't
sense,
the way
right?
to think of it. The way to think of it is so stupidly dense that you might as well consider it a solid because its density and your density aren't that different. Now, let me rephrase that. Its density is much, much greater than your density.
Right.
So,
you have gases, or what would normally consider to be gases, and there's like 7 different kinds of water ice, depending on the pressures and the temperatures and the phases that it's at.
But
down through the
thing is that the centers of these bodies are so dense and so hot that rocks. You're not talking about rocks at this point. What you're talking about potentially is some sort of a crystalline structure or gases that behave following gas laws but are so dense that you might as well think of them as chunk O planet versus gas, wave your hand through it.
Right, but I think, when a lot of people, when they pose that question, they have this vague hope, that you could sink down through Jupiter and then land on the planet below.
It's much more a matter of sink through its atmosphere until you get crushed.
Yeah, or superheated to hundreds of thousands of Kelvin and pressures that are millions of times what you would experience on the surface of the Earth and land.
No, you just get crushed.
Yeah, you get crushed. So
rocky solid, not the. If you think about the density of rock versus the density of the inner layers, sure, I'll give you that. But in terms of behaving like a rock, no, it's just too hot.
Yeah. Rod Mole asks, and I should have talked about this a little bit more. Does our atmosphere have an effect on the seasons?
It's part of that lag that we experience. Is our atmosphere is a blanket that holds in the temperatures. So when we experience the re-radiation lag from the soils and the water radiating the heat that they'd stored up, our atmosphere then also helps by reflecting not a lot, but a fair amount of the infrared back down towards the planet. We don't have Venus's global warming, at least not yet. And as long as some of the infrared manages to escape, we're good. But it is reflecting some of the IR back down and helping us retain our heat.
Prime Navigator asks, how does the Gulf Stream affect weather? I know it allows places like Ireland to have palm trees. And what would happen if the stream were to disappear? Palm trees in Ireland, really?
Well, they're not.
We have some palm
trees
trees here, actually.
It's think more yucca. I've seen yucca in England, and it really confused me. So what ends up happening is there's this mid-ocean conveyor belt that is driven by the temperature differences between the tropical latitudes and the extreme north, and it's also aided by the salinity. So if our ocean wasn't a saltwater ocean, we wouldn't have this mid-ocean conveyor belt. And one of the concerns is that if we change the salinity of the ocean too much, then we shut down this conveyor belt. Now, right now, what it's able to do is cold water sinks, flows down to the tropics, um, and cycles up to the surface as part of this conveyor, gets heated up. The hot water then flows north, radiates its heat around, well, places like England and Ireland, sinks back down, and so you have this conveyor belt transporting the heat. Now, we see similar streams, the jet stream, the Gulf Stream, atmospherically, but they're driven by different physics. Atmospheres and ocean currents aren't identical. But this is where we get things like the Arctic blasts coming down from Canada and making Chicago far more miserable than Boston. And so we do have to pay attention. Where I live in St. Louis, the jet stream likes to switch between being north of us, in which case we get weather similar to the city of Dallas, and being south of us, in which case we are almost as miserable as people in Chicago, but not quite. And so it's that movement of the jet stream that deeply affects our weather in the winter.
So here is a great question. This comes from Detlef Crows. What could explain the irregular seasons in George R. R. Martin's Song of Ice and Fire series? Now, have you read like Game of Thrones and those books?
So I don't.
Right, so they always say like winter is coming, right? And so the
Right.
idea in this is that you have these irregular seasons of summer and winter, which can last for many years. It can last 6, 7, 10 years. When the season switches from summer to winter, it can be, quite unpredictable. So they never really know, when that's going to happen. So I guess the question is there some kind of natural situation that you could end up with, irregular length seasons that maybe difficult for astronomers to predict how long these seasons are going to last.
Well, they don't exactly have high technology in those books.
Right.
But
so in other words, maybe there is some math, but in the
well, so the piece of information that I don't remember seeing in the books is whether the length of the day varies between summer and winter. If the length of the day isn't varying between their superimposed really large seasons, then it can be caused by having a highly elliptical orbit that is an irregular orbit due to interplay with other planets in the system. So if you imagine that there's a couple of large giant planets, that you end up with this it would be periodic, but very hard to figure out periodicity to your orbit.
Could you have some situation that's maybe changing the, like with our Earth, we've got this axial tilt that's at this very set direction, and that's, in many cases what's, when, here's the sun and the Earth is over here, and then it's over there, and it's over here. But I guess, could there be a situation where you could get some kind of precession from the direction of the
issue is
at the same time that you've got some kind of elliptical orbit, and then that would really...
The issue is all of the precession type things are fairly periodic, so the fact that they can't predict, it indicates that there has to be interplay with some greater system. Now, without a moon...
torque that you mentioned earlier on, right? You have some kind of torques that are pulling the planet into different orientations.
And if you don't have a moon, that's easier to do.
Right. And so if you had some weird combination of an elliptical orbit that gives you that closer, farther from the sun that we talked about, and then you also had something that was causing this torque on the axial tilt of the planet, then you get these combinations. You get severe winters, you'd get no winter, you'd get severe summers of varying lengths depending on the interactions between all the
it would just be the interplay between all the different systems. And what's interesting to think about is at one point in our own solar system's evolution, the outer gas giants were extremely interplaying with one another as they went through different resonant orbits, and this essentially flung Uranus and Neptune to the outer solar system. They didn't start there. So during the birth of a solar system, you can have great amounts of planetary migration, a lot of interplay between the planets, and this may simply be a young world.
That is really
but then they'd probably have a lot more asteroid impacts, so that was probably a dumb statement.
Right. Oh, and then Jens Riggleson mentions on YouTube that the sun could be an irregular variable star, and so you could get as an addition that the sun is putting out different amounts
Now,
of energy, right?
if that was true, you'd also get a lot of color variations, and that's the type of thing that I think would be mentioned because it would be desperate color variations.
Because you get different amounts of energy coming out of the sun. Yeah. Um, but would you? I mean, are there variable stars that have that level of irregularity?
Oh yeah,
Yeah.
Myra
Okay.
variables do.
Yeah. Okay.
But
But I know
but
with the Mira variables, it's fairly fast, right? I mean, they kind of
no,
puff out and then
no,
they could
that
change
you're
their
thinking of like RLRs and stuff. No, Myra
right, right, okay,
variables are year to years, but most of them are order of a year. But giant red variable stars can have very long periods. The issue is giant red stars have already bloated up and eaten their solar system.
right. But I think there are some legit ways that you could have a world that has an irregular season.
Yeah, well, no, I don't think irregular star makes sense given the
No, no, no.
universe he's
For
defined.
all of the things that we talked about. I mean,
Yeah,
again, if you add, if you have even minor variations in stellar output, I mean, if you're, it doesn't have to get to the point that it's changing temperature. It only has to be putting out 75% or 90% of the energy. That would still have a dramatic effect. That would
that
give
would
you
destroy the
winter.
planet.
Oh,
That's a
okay.
little too
Oh,
extreme.
sorry, 90, yeah, so 95%, 98%, right? I mean, it's like not a big difference, and you're going to get these big variations. So anyway, add weird orbits, crazy axial tilt, torques from other planets, and stellar variation. I think we've got a recipe for George R. R. Martin. It would be nice if he had, I guess, talked to you first, Pamela, so you could help him work out the math. But
He's rolling in so much money it doesn't matter.
yeah, he doesn't need it. Um, Cool. Well, I think that was great. Thank you very much for taking the time to do this show, and thanks for everybody for sticking around and watching the after show.
My
Now
pleasure.
we've got to record a weird episode this week because you're going to be gone
Next week,
next week,
yeah, I'll
right?
be at the AGU meeting for any of you out there who might be in the San Francisco area.
Cool. That's a good meeting. I'm sure Emily's going to be there, right?
I don't
She's
know. I think
really
so.
she's
Yeah.
she's a geophysicist,
Right, but
planetary
she has small
geologist.
children who are very cute, and most of the
I
information
think
is
she
available on
mentioned
the internet.
I think she mentioned that she would be there. But anyway, um, right. Okay. So we're gonna do another show probably what Wednesday, Thursday. When do you want to do that?
I'm thinking Wednesday, Thursday, and Friday. I'm in
Okay.
meetings all day.
And we had proposed the topic of climate change.
Yes.
This will be
Let the
fun.
hate mail
Let the
begin.
hate mail begin. Yeah. So yeah, we'll do an episode on climate change later on this week. So I'll put the time when we decide on a time. I'll put that into the calendar and set it as an event, and
Okay.
we'll do that. Cool.
Okay.
Awesome. All
Sounds
right.
good.
Well, thank you once again. Thanks everybody watching, and we will see you on the next show.
Sounds good. Talk to you later. Bye bye.